Welcome to Electronic Seed YouTube channel. Today in this video we will learn about static timing analysis. Let's get started. Static timing analysis verifies a circuit's timing behavior without actually running logic simulations. It doesn't need input vectors because it mathematically evaluates every possible timing path in the design. The tool computes propagation delays and checks whether all timing constraints are satisfied. The term static distinguishes this approach from dynamic simulation, which applies specific input patterns. STA analyzes all timing paths simultaneously and exhaustively, leaving no path unchecked. This method is highly scalable, so it works even for designs with millions of logic cells. STA is typically performed after placement and routing are already complete. It extracts accurate parasitic resistance and capacitance values from the routed layout. Performance specifications must be established before chip design actually begins. For example, a target frequency of 3.2 GHz gives a clock period of about 312 picoseconds. Every signal path in the chip must complete its propagation within that narrow window. These early goals are called timing requirements, and they drive synthesis, library selection, and floor planning. STA then answers the key question: does our physical design actually meet those requirements? If yes, we can proceed to tape out with confidence. If no, we must resolve the violations through optimization loops. The fundamental structure that STA evaluates is the path from one flip-flop to another flip-flop. Data is captured at the flip-flops on each clock edge. Between two consecutive flip-flops, there is combinational logic that STA must analyze. Two flip-flop parameters are especially critical for timing. Setup time is the minimum time data must be stable before the clock edge arrives. Hold time is the minimum time data must stay stable after the clock edge. For instance, a flip-flop might have setup time of 80 picoseconds and hold time of 40 picoseconds. If data arrives only 50 picoseconds before the edge, that is a setup violation. And if data changes within 40 picoseconds after the edge, that is a hold violation. When a setup or hold violation occurs, the flip-flop can enter a state called metastability. In this state, the output cannot resolve to a stable logic 0 or 1. It might oscillate, settle at a mid-level voltage, or resolve randomly. This makes the circuit's behavior fundamentally unpredictable. STA prevents this failure mode by ensuring violations never happen in silicon. STA systematically analyzes every timing path in the design. It identifies the path with the longest delay, which we call the critical path. That critical path determines the maximum operating frequency of the chip. The total delay includes T clock to Q, the clock to output delay from the source flip-flop, plus T logic, the delay through the combinational logic, and finally T setup, the setup time required by the destination flip-flop. By calculating these delays for every path, STA determines several key results. First, the maximum operating frequency the design can support. Second, all paths that violate setup or hold constraints. Third, the slack on each path, which is the margin between actual and required arrival time. Positive slack means timing is met and the path is safe. Negative slack means a violation exists and must be corrected. If we see negative slack, we enter the timing closure loop. This is an iterative process of targeted optimization until all violations are resolved. At the synthesis level, we have several strategies. We can replace cells with faster variants from the library, or restructure the logic to reduce the depth of the critical path. Inserting buffers can also help balance skewed paths. At the placement level, we use different strategies. We can reposition cell to shorten the interconnect wires. And we improve proximity between blocks that communicate frequently. At the routing level, we have additional strategies. We can use wider metal layers on critical nets to reduce resistance. We also apply net-specific constraints to manage parasitic loading. The whole process repeats. We run STA after each optimization pass. Our goal is non-negative slack across all operating corners. Those corners include variations in process, voltage, and temperature, collectively called PVT. Exhaustive dynamic simulation is simply impractical for complex system-on-chips or ASICs. Modern chips contain hundreds of millions of sequential elements. STA covers all timing paths simultaneously and deterministically. At multi-gigahertz frequencies, timing margins become extremely narrow. Even small routing parasitics can cause marginal paths to fail. STA combined with sign-off quality extraction provides the required accuracy. As we scale toward 3 nanometers and beyond, STA's importance only increases. Tools are evolving to handle increased process variation. Multimode multi-corner analysis, or MMMC, is now essential. Advanced interconnect modeling is required at these small nodes. Machine learning-assisted timing prediction is emerging. ML can help accelerate the timing closure loop. Despite these changes, STA remains foundational for performance, reliability, and correctness.